We're going to do a brief example involving a pressure vessel just to illustrate how the equations work. What we have here is an air compressor that is acting as a pressure vessel. The air inside is pressurized to 90 psi, and there is an internal diameter of 22 inches with a wall thickness of 0.25. So that means the outside diameter would be 22.5 inches. Now the first thing that we can notice is that this is a thin-walled pressure vessel, and we can demonstrate that by computing R over T. R over T is going to be 11 inches. Oops. 11 inches divided by 0.25 inches. And that gives us 44, which is greater than 10. So we can proceed with the assumptions that we have that state that assumption mainly being that our radial normal stress is equal to 0. So proceeding forward, we're going to want to calculate two things, our hoop stress and our longitudinal stress. We know that the equation for our hoop stress, which is the stress that goes around the cylinder, or sigma theta, that is equal to PR over T. In this case, we have a pressure of 90 psi. The radius is 11 inches, and the thickness is 0.25 inches. And so that equals 3.96 KSI. Now the stress in the other direction, our longitudinal direction, we'll call sigma z. That is PR over T. That's 90 psi times 11 inches divided by 0.25 inches. Excuse me, PR over 2T. There we go. So that ends up being half of our hoop stress. So this is 1.98 KSI. And that means if we look at a material element that has its sides, so a little volume element, to have its sides aligned with the Z theta, theta is actually going to be down here. This will be our theta direction. Then what we're going to see is that the stress in this theta direction is a tension of 3.96 KSI, and the stress in the other direction, the Z direction, is 1.98 KSI, and those are the only stresses generated by the internal pressure on an element acting in that orientation.